right, well today we're going to combine different functions through addition or subtraction at the top. Then we're going to move down in the middle to multiplying two functions together and dividing. And then we're going to do some combining at the bottom. So let's start with just adding and subtracting functions. You can see at the top in the directions, they told us what f of x equals. I put that in red parentheses. G of x I put in blue parentheses, and h of x I put in green parentheses. So if we go to our first problem, they're asking us to add f of x, which is the 7x to the 1/2 power minus 2. And they're asking us to add that to g of x. So what I want to point out to you is we are adding, not multiplying, exponential expressions. So if you go back to the very beginning when you first started adding terms together, you'll remember they had to be alike to add them together. So for example, if I come out here to the side for a minute, let's pretend that 7x is not to the 1/2 in that problem. Let's say it was just squared. I'm just going to change it just to show you. I know that I can add that to something that also has a like exponent. So if I change this negative x to the 1/2 that's in blue here, if I just made that as well as squared, that looks a little more familiar to you. It should, because you've been doing this for quite a while now. The terms are alike, and so because they're alike, you can combine them. And remember, when I say combine, I'm meaning either adding or subtracting them. We're not multiplying and dividing here. The exponent rules change there. But when you are adding or subtracting, you are only going to be adding and subtracting like terms. So over here, we've got a 7x to the 1/2, and we have a negative x to the 1/2. They're alike. Those terms are alike because the exponent, the bases match, the x, and the exponent matches of 1/2. So we can say 7 of those minus or plus a minus 1x to the 1/2 would give us 6x to the 1/2. And then we have two constants. We have a negative 2, and we're going to add to that positive 4 to give us a positive 2. All right, if we do the same thing on number 2, but now I am adding together f of x, which once again is the one in red, and I'm going to add to that h of x, which is the one that's in green right here. Now my parentheses don't matter a whole lot right now because we're adding, so we're not going to have any sign changes. It's going to matter more down here in 4 and 5 that we keep those parentheses together until we're ready to actually combine. So we're going to look for like terms. Again, we have a 7x to the 1/2 that matches this negative 4x to the 1/2. Again, we're combining through addition. We're not multiplying here. So we can just add the coefficients and keep that exponent and that base and exponent the same. So we had 7 x's to the 1/2. We subtracted 4 of those x's to the 1/2 away and ended up with 3 x's to the 1/2. And then we go in and grab our constants, a negative 2 plus that negative 1, of course, is a negative 1. So now we're going to go to 4. We're going to do the same thing we did in 1, except now we are subtracting them. So this is where the parentheses, especially on that second function, becomes more important because we want to remember that the sign change, because we're subtracting, has to happen on both of those terms in that second function. So I've got this red function. I'm going to subtract the blue function from it, so I'm going to change the signs. And now it's an addition problem, and now we're doing the same thing again. I'm looking for like terms. So I have 7 x's to the 1/2 and another positive x to the 1/2. So I'm going to add the 7 to the 1 to give me 8 x's to the 1/2. And then I go and do the same thing with my constants because they are also alike. Again, keep in mind we are adding here. We're combining. We're not multiplying. We'll do the same thing on number 5. We're going to, this time, go with the green function of h of x. And we're going to subtract from that f of x, which is the red. Right, we are subtracting here. so we have to go in and change signs. So this is going to change to an addition sign. Every sign after it is going to change to the opposite of what it was. And then I'm looking for like terms. So I've got negative 4x to the 1/2 here, negative 7x to the 1/2 there. So we're going to combine those two negative coefficients to give us negative 11 x to the 1/2, and then we'll combine those constants to give us a positive 3. Okay, just a couple things to remember from this section. When you are adding or subtracting, you combine like terms just like you do when you combine something like 2x squared plus x squared to give you 3x squared. You're adding the coefficients together, but the base and the exponent stay the same. All right, that's what happens when you are either adding or subtracting. When you are subtracting one function from another, the subtraction sign changes the sign on every term after it. We've been dealing with this quite a bit already this year, so this should sound familiar. So it's the same deal that we've been dealing with on all the other kind of problems before it. Take a minute to pause the video and write this down, especially if these are two rules that you struggle to remember. Just take a minute to write down your worksheet so that when you go back to use this for your homework, you've got it in front of you. All right, now moving on to the middle of the worksheet. Here we are moving into multiplication and division. So the rules for our exponents change when we multiply or divide. They're not going to be any different than what you've already been accustomed to. It's just now we're dealing with exponents that are fractional, so it can look a little bit different and maybe feel a little bit different for a while, but you're going to follow the exact same rules that you've been following all along. All right, so in number 7, again, we've got 3 functions. We have a 4x squared, which is f of x. We have a negative 3x to the 4/3 power for g of x, and our h of x is x to the 1/2. So now we are multiplying. I'm going to write my f of x, which is 4x squared, and my g of x, which is negative 3x to the 4/3 power. All right, so when we multiply exponential expressions, the rule has always been, and it still is, that we multiply the coefficients together. So in this case, the 4 and the negative 3, we multiply together to get negative 12. Then we take the exponent, the exponential part with the variable, we take the base and rewrite it, and we add the exponents, right? So in this case, we end up with 2 plus a 4/3, okay? So you can either change that 2 to have a denominator of 3, so we could say 6 over 3 plus 4 over 3, or you can think of 4/3 as 1 and 1/3. So what we're doing is we're just going to be combining those. You can't leave it like that. So I'm going to come out here to the side and show you that we have to combine 2 and 2 plus that 4/3. So we can either think of the 2 as 6 over 3, and we can add 4/3 to it to get 10/3, or you might think of it more as like 2 plus 1 and 1/3, which is going to give us 3 and 1/3, which is actually, once again, 10/3. When we write it as an exponent, we're going to want to write it as 10/3. How you get to 10/3, whether you go to a mixed fraction, a mixed number, then to an improper, or if you just go straight to that improper fraction, doesn't actually matter, but we do want to write it out as an improper fraction. We don't want to have a mixed number up there as an exponent. All right, so on number 8, we're going to do the same thing, except now we're multiplying 4x squared times our h of x, which is x to the 1/2. All right, but we're going to follow the same exponent rules that have been true up to this point. Multiply the two coefficients, 4 and 1, and we're going to get 4. Rewrite the base, and we're going to add the exponents. So once again here, we have a whole number that we have to add the 1/2 to. So really right here I could write 2 plus a half for my exponent. So that is going to be 2 and 1/2. So I'm going to go to a mixed number first, just because it's easy, and then I can easily convert that to that improper form of 5 over 2. So simplified, this is going to look like that. All right, same deal on number 10 and 11. This time we're dividing. So we're going to have 4x squared divided by negative 3x to the 4/3. It looks weird, it looks a little bit scary, but let's just follow the rules. So the rules have always said when you're dividing exponential expressions to divide the coefficients. So here we're going to divide 4 and negative 3. I'm just going to pull that out and leave it like this. I mean, I'm not going to get the decimal. We'll just leave it as an improper fraction. And then from there, we've always rewritten the base, and we have subtracted those exponents. So now we have 2 minus 4/3. So once again, I'm going to come off to the side, and I just need to actually reduce that, or subtract that. I can do the same thing. I can rename 2 as 6/3 so that they have the same denominator. That's probably the easiest way to do this one, because then you go straight to the fractional form, which is 2/3. So in order to have this in the most simplified version of itself, it'll look like that. Right, on number 11, we have x to the 1/2 divided by 4x squared. So we're looking at the coefficients. We're going to divide the coefficients. We know it's not actually written here, but you know that coefficient is 1. So you can see the 1/4 just kind of pops out. So we've got a 1/4 coefficient, and then rewrite the base. I'm going to subtract, that's not what I meant to do. That should be 1/2 minus 2. All right, so come out to the side. So now you can see I'm going to end up with a negative exponent. All right, so I'm going to take this 1/2 and I'm going to subtract 2 from it. I'm going to call 2 4/2 so that they have the denominators that are the same. So I'm going to end up with a negative 3/2. And that's okay, we have some more simplification to do. So here we have 1/4. I'm just rewriting everything in the simplified form. We know we do not want a negative exponent, though. We can't have a negative exponent in our final answer. So I'm going to take that x to the negative 3/2 and I'm going to flip it down into the denominator with that 4 and make it positive. So that leaves me with just that 1 up in the numerator. If that one is a little confusing, maybe rewind and watch it one more time. I think that if you see it one more time, you're gonna be better off probably. The reason this one's a little bit tricky is because we have that 1 in the numerator to begin with, which gives us that 1/4 coefficient. That's a little tricky, and then on top of it, you have end up with a negative exponent. So if you didn't get that the first time, just rewind a minute here and watch that again. All right, and again, a couple of things to remember. If you're multiplying or dividing exponential expressions, then you're either going to multiply or divide the coefficients. Rewrite the exponential base next. Then add those exponents if you're multiplying terms. If you are dividing, then you need to subtract those exponents. And then in the end, make sure that that's simplified. And then if it's a negative exponent, you need to reciprocate it either into the numerator or denominator to get rid of that negative sign on that exponent. So on 13 and 14, what we have going on here is called a composite function. So you're taking one function and you're plugging that function in for the x on a separate function. So in number 13, there are 2 functions there. Well, there's 3 in the directions, but in 13, we're just dealing with f of x, and then we're going to deal separately with g of x. And the way we're going to put those 2 together is out here, they tell us that they want us to write out f of x with g of x substituted in where the x is. So we're going to take g of x, this little function here, and we're going to plug it in where we have, see, x the x variable in the f function. So if I were going to write that out, it would look like this. I would take my f of x, which is 2x plus 3, but instead of writing x, I'm going to instead fill in the g of x function. All right, so take a minute to look at that. And I really, out here, I should write what they asked us. And remember, this side is just really for information. I'm not doing any multiplying or anything over there. So what that tells us that we want to take g of x, that 3 over x plus 1, anywhere where we see an x variable in the function f, we're going to plug that function in, that g of x function in. And then from there, we just do the algebra on it. So we'll multiply the 2 and the 3 together. Okay, so I'm just multiplying. 2 is really, over 1. So I'm multiplying the numerators and the denominators together, and I end up with this. Okay, and then we have to remember how to add two fractions together. In this case, these two don't have the same denominator. So I have a 3. I need to have that x plus 1 in the denominator. So here's how I do that. Just so that I can add them together. So the way I'm going to do that is I'm going to rewrite that 6 over x plus 1. I don't need to do anything with that one. I'm going to make the numerator, the denominator with my 3 be x plus 1 as well. But I can't just stick x plus 1 in the denominator. If I'm going to put it in the denominator, I have to also put it up here in the numerator, because then the two of those together, x plus 1 over x plus 1, is like multiplying 3 by a version of 1. We're just changing, I'm just changing the form of 3 to a fractional form, but I'm not changing its value because I'm multiplying it by x plus 1 as well as dividing it by x plus 1. So in essence, I'm just kind of multiplying them by 1. All right. If that doesn't make sense just yet, that's okay. We're going to talk about this. We'll be talking about this for a while. So just see if you can follow along here. At this point now, I'm just going to be simplifying. So I'm going to distribute that 3 to the numerator. End up with this. And now they have like denominators. So because of that, I can add those numerators together and put it all over the same denominator. That's really similar. It looks very strange because we're dealing with all these variables and these binomials in the denominator. But I mean, if I had 6 over 10 was my fraction plus 3 over 10, that maybe helps jog your memory that as long as the denominators are the same, I can add those numerators together, put it over the similar denominator, and get a fraction. So that's what I've done over here. Looks very odd because of just the forms of these numbers we're using. And that right there is as simplified as we can get it. So that's your final answer. All right, once again, if you didn't quite catch it the first time, go back and watch it one more time before you move on to number 14. All right, same idea in number 14, except now they have the g of x is on the outside here. So I know from this that every time I see an x in the function g of x, so I see that variable x down here in the denominator, when I see that, I'm going to plug in h of x. That's what the number 14 is telling me. Plug h of x in every time you see x in the g function. So that's going to look like this. There's my x, and I'm going to plug this whole thing in to there. So if I rewrite that, what that looks like is I'm going to start with the g of x. Let me write my function notation out here, showing the combination. And then I'm going to put that 3 in the numerator. We don't need to change anything there, but then that x in the denominator, I'm not going to write that x. I'm going to write in this x plus 5 over 2. I'm going to put that in parentheses because we've got to do some stuff with that. and then the g of x says to add 1 to that. All right, so now I have a numerator that's pretty much simplified. I can't do anything there. I do need to take care of this very complicated denominator. However, again, I have two fractions that need to be added together. I've got an x plus 5 over 2, and I have a 1. Well, if I want to make those both have the same denominator, I'm going to change my 1. I'm going to put a 2 in that denominator. Okay, and if I put a 2 in the denominator, well, then I've got to multiply it by 2 up here as well, so that I don't change the value of the number 1. All right, so 2 times 1 is just going to give me 2 here. So I'm just renaming that whole number 1 as 2 over 2 with the sole purpose of getting the denominators to be the same. The reason I want the denominators to be the same is because now I can combine the numerators all over the same denominator. And now I end up with x plus 7 over 2 as the denominator, which probably doesn't sound much better. So right here, this is only the denominator. I'm going to come back up here now because I don't want to forget about that numerator. I was just trying to get that numerator out of the way so we could deal with this denominator. So that probably doesn't look a whole lot better until you think about what is really going on here. What's really going on here is, if we go way back, I mean, you've been doing this for a long time, 3 divided by x plus 7 over 2. That's what really is happening right here. If we just put it out horizontally, it's a little bit easier to see it. And so we know if we are dividing two fractions, in this case a whole number by a fraction, we change the division sign to a multiplication sign, and we reciprocate what the fraction that is after the division sign. From here, we know 3 is really over 1, so we're going to multiply the numerators, multiply the denominators, x plus 7 over this 1 that does exist under the 3 there, and that is our final answer. So very complicated things that we're dealing with here. However, they are following the exact same basic rules that have been true, that you've been working with all the way since pre-algebra, through Algebra 1 and into the exponent rules that we've been dealing with this year. So the basics are the same. It's just you have to be able to put all of it together in this one complicated idea. All right, moving to the back of the sheet, we are adding the functions together that they've given us. So once again, in the directions, they've defined 3 different functions. In number 19, which I may or may not have circled on yours, but we're going to do 19 and 20. We're going to add f of x, which is 3x plus 2. I'm getting that from right here, to g of x, which is just 2x squared. All right, and we're just adding the two of them together. There are no like terms there. You should be able to hopefully see that that's a quadratic, that's a trinomial. I'm just going to rearrange the terms so that they are in descending order of degree. And there's that final answer. Now, they ask you to state the domain of the operation. So what that means is what x's are okay, will satisfy this function right here, this 2x squared plus 3x plus 2. And the thing that we're looking for here especially is that we don't, this one isn't really a problem, because really we can stick any x in there and get a legitimate y out. So the answer to what is the domain here, what can the x's be, so would be all real numbers. Okay, it's going to become a little more obvious when we do 20 why this one is all reals. Okay, we can put any real number in for x in this function and get a corresponding y out that is also a real number and not a 0. Okay, so if we do number 20 though, number 20, we have, it's a more complicated. We've got h of x, and here we're going to subtract. So I'm going to put it in parentheses because we've got more than one term in f of x. So because of that, I'm going to put it in a subtraction sign so that I remember to change each sign after it when I get to that part. Okay, so I've got a fraction and I need to subtract a non-fraction from it. All right, so because of that, I have to go back to the idea of making like denominators. So I want both the denominators to be x plus 3 because I've already got x plus 3 here. Over here, I just have a 1. You know, this is really just sitting over 1 like we've talked about for a long time now. If I want to do that, if I want them to be the same, then I need x plus 3 down here, okay, which means if I want that to happen, then I'm going to multiply by x plus 3 down here. If I do it in the denominator, though, I've also got to multiply it up here in the numerator because now I'm really multiplying by 1. X plus 3 over x plus 3 is really 1. And so I'm not changing the value of the fraction, I'm just changing the form of it so that I'm able to combine these two. All right, so I'm going to rewrite the negative 4 over x plus 3. And I'm going to put the subtraction sign in there. I'm going to take care of this multiplication. We're going to end up with this binomial times this binomial, all sitting over 1 times x plus 3, which is just x plus 3. And this is what we wanted. We wanted those two denominators to match. All right, so now you got to look at the problem and say, I'm trying to simplify them. Before I can do any subtraction, I have to take care of this numerator. I have two binomials, and you know how to take care of two binomials. We're just going to FOIL. So I'm just going to keep writing this fraction, even though we're not doing anything with it yet. If I FOIL here, I'm going to end up with 3x squared plus 9x plus 2x plus 6. All of that, once again, is sitting over x plus 3. All right, now I know I can combine this 9x and the 2x. I'll go ahead and do that, but I'm going to do it all in one step. I'm going to take these two numerators here, and I'm going to put both of them, and look, I'm going to go ahead and make this 11x here. No, I'm not. Yeah, yes, I am. And all of that goes over x plus 3. Now I'm going to take care of that subtraction sign up there. So, oh, and look, I'm going to box this in just so, no, I'm not. What am I doing? I got rid of that already. Sorry. I'm going to go ahead and take care of that subtraction sign. So the subtraction sign is going to change the sign on everything after it. Now I can go ahead and combine any like terms up there, which the only thing we have that's alike up here in that numerator at this point is those two constants. So negative 4 and negative 6 will give us a negative 10, and all of this is sitting over x plus 3. This is as far as we can go with simplification. Everything is simplified. And now we can talk about the domain. So the domain, in this case, we've got x's in the numerator and we have an x in the denominator. So we have to really think about this x in the denominator. That's the constraint that we have on the domain. If we say all real numbers could go in here for x, the problem is that if we put a negative 3 in here for x, we're going to end up with a 0 in the denominator. And hopefully you remember from years past that you can't divide by 0 that is undefined. You can divide 0 by a number, so you could have 0 in the numerator, but you cannot have 0 in the denominator. That's undefined. So the answer here for what the domain is all real numbers except negative 3. So what we're really looking for with this domain, like I said, in the number 19, because we're not dealing with a denominator, if you don't have a denominator, the domain is always going to be all reals, because there's really not any other constraint that can be on that. The problem here with this one is if you've got a denominator, you've got to look at that denominator and say, is there any number that if I stuck it in at x, it would give me a 0 in the denominator. And if that's the case, that number needs to be taken out of the set of all real numbers for the domain. All right, and last, hopefully we can move this through this a little bit quicker. You have a coupon for $200 off the price of a computer. When you arrive at the store, you find that the computers are on sale for 20% off. They want you to let X represent the original price of the computer. So 25, use a function notation to describe your cost, f of X, and you remember X is going to be the original cost of the computer. This function they want you to write out if you're only using the coupon. So if X is the original price of the coupon of the computer, and then we have this $200 coupon, then we would just say X minus 200 to describe, this would be a function that would describe our cost if only using the coupon. 26 asks you to do the same thing, only this time call it g of X, and this is going to be the case if you only use that 20% off discount. So if X is the original cost of the computer, our cost, g of X, is going to be 0.8 times the original cost. It's not 0.2 because 0.2 is just the discount. So that would give us how much off of the computer we're getting. They asked us to write it to describe our cost. So our cost is going to be 80% of the original, which is that 0.8. Remember, you have to put percentage signs as a decimal. This percent sign doesn't really mean anything. It just means 20 out of 100. And so we have to turn that into a decimal if we're going to use it. So, but in this case, we wanted the 80%, which is why I got the 0.8. In 27, now they say form the composition. So that means like what we did on the front side of the sheet on the bottom, form the composition of the functions f and g that represents your cost if you use the coupon first and then take the 20% off discount. So if we use the coupon first, that's our function f of X. We're going to use that first, and then we'll get a number, and then we'll take that number and we'll multiply it by the discount, the 0.8. All right, so we're doing the coupon first. That's what they said, coupon first. That's why I'm taking X minus 200, and then I'm going to take that number and multiply by 0.8. So if I were to write out that composition with using the letters, that would be X minus 200 is our f of X, and we're taking f of X and we're sticking it in as a composition of g of X. 28 tells us to do the opposite, form the composition of the functions f and g that represents your cost if you use the discount first. So if we use the discount first, we're talking about g of X. We're going to take 80% of it first, and then we'll subtract the coupon off. So this composition is represented by what we did first. First we took g of X, right, because g of X is that 0.8 X, and then we combined that inside of the f of X. So this is read f of g of X, and number 28. Number 27 is read g of f of X. So 29 asks, would you pay less for the computer if you used the coupon first or took the 20% discount first? So probably the easiest way to show this is just to pick a random number for the original price of the computer and evaluate in at each of these. So if I, let's say that the original price of my computer was $1,200. So if I stick $1,200 in and evaluate that here, I end up with 0.8 times 1,000, which we know that's going to end up being $800. Okay, and we'll compare that down here. If I take the 80% first of the 1,200 and then take away 200, well, 80% of 1,200 is $960. Then I take that 200 away, and I end up with $760. So just a simple illustration there shows you that if you take 80% of a number first, you're going to get a smaller number, and then you take 200 away from that, that's going to be the better deal in the end. So the answer here is it's better to use the discount first and then the coupon.